Hi, welcome back to the part 3 of how to implement efficient RAG. So in previous video, we discussed about this data indexing. In data indexing, we learned how to create your data sources, how to make them noise free, how to make them structured. We discussed about various chunking strategies. We used embedding models to create embeddings. We created vector store, and we discussed about various indexing parameters like cosine or Euclidean. Now we have our data store created. The next part would be the retrieval. How to retrieve data out of your RAG system. So in this video, we are going to discuss this part. Now actually we are into the RAG, this RAG stuff. So the first part, the officially first part of the RAG system is retrieval. So in this retrieval part, we will see various types of retrievers. We will majorly discuss two, dense retrieval and hybrid retrieval. And we will see how a query expansion can certainly improve the results and the accuracy of the results we are getting from our RAG pipeline. And also we will see some re-ranking strategies, how to further refine your results. These are coming from your retrieval, whether you use dense retrieval or hybrid. And at the end, context is very important. The RAG system, if you ask it some questions, it will definitely give you some answers, but these answers might or might not be according to your context. So let's get started and jump into the code. Yeah, so in the same project in the GitHub, I have created a new notebook that is called part 3, retrieval strategies. So in this notebook, we will be having some pointers about the theory and some coding samples as well, whatever we have seen in the diagram in our design here. So to proceed with any kind of retrieval, we will have to make our vector store first. So this semantic chunking function I'm going to use to create the chunks of the data. If you remember from the previous episode, that is a sample data for a corporate remote work policy. So using same data, we will create semantic chunking. This is a repetitive step from the previous episode, and we will then build a vector store out of the chunks which we have created in this step. So these two steps are necessary to proceed with our retrieval in this video. So I will execute the cell, this one first, semantic chunking. I will not go into the depth because we have already discussed this in detail in the part 2. So I'm just going to execute the semantic chunking. Just to keep it short, for the people who have missed the part 2, we are creating chunks not based on sentences, words or paragraphs, but we are making chunks based on their semantic similarity. So the similar kind of textual part out of our full document will remain in single chunk. That's the very brief, but if you really want to get into the depth of this, how we create it, you can see the part 2. So I'm going to directly run this. Now the chunks are available. In the next step, we are going to create the embeddings. So I will just run this again. It will take a while to execute, a few seconds it took, and it has created my vector store in this object. So whenever I want to query, I'm going to query this collection object every time. This is my vector store, and again how it is created, that is discussed in detail in part 2. So our retrieval starts here. So there are various kinds of retrieval strategies we will discuss. There are majorly two. One is dense vector retrieval or dense retrieval. This is a direct query which is executed on the vector store. There is no additional step. And another is hybrid approach, where we retrieve using two methods. One is this dense retrieval, and we will use BM25 keyword matching mechanism that we will discuss after the dense retrieval. Let us have a look what is happening here. It's very simple and most commonly used retrieval strategy. For example, you have this function, you take query, This top k is very important because here you tell that how many results you want to retrieve out of your vector store, the best matching results, and then here in this line the collection and the query function will give you that many results. It takes this top k, top 3 results for example, so it will return you the 3 results which are matching best according to your query. So for example, here is the execution part. Your query is what are the internet speed requirements for remote work. Now you want to search this query semantically. Semantically is a different thing than keyword matching, which we are going to discuss in the next cell. So we are going to search the parts in the text which are similar to this, which have the similar meaning. And here we are passing this query along with the top results we are expecting. Let me put a breakpoint and let me run this in debug mode. So we have received results, and if I hover the mouse here, you can see there are exactly 3 results I have received. And this is important, the distance. You see a list of some floating numbers. So this is the score. While the retriever executed on your vector store, it created a score that is called distances. The distances is like this chunk 4, chunk number 4 achieved this distance, means this is this far away from your user query in the vector store, in the multi-dimensional vector store. What are the dimensions? Again, that we have discussed in detail in part 2. So these are the distances of various 3 chunks from your user query. So here just the print statements. Look at this statement. What we are going to do, we are just reversing this distance to the similarity score. What do I mean to say is, if your distance is higher, is bigger, it means you have less similarity to that chunk. So we are just reverting it. This number, by the way, can be between 0 and 1. So we are just subtracting it from 1 so that it gives you like similarity score. This will become like, if you have bigger similarity score, your result is more close to your query. So this is just a reversal, and this will be useful in the hybrid search, which we are going to discuss next. That's it, and we are good to go. We have retrieved, we have implemented our first retrieval code. One more important point to note here is query embeddings. So query, how to retrieve results from your vector store according to your query. So we will have to convert our query also into embeddings or vectors. So this single line does that. So we are comparing vectors against vectors. So this is not like text against vectors. So query also converted to vectors, and then we already have a vector store, and the query is fired on your vector store to get the most matching results, the top 3 results. That's it. Now if I remove the debug point and just run this cell, have a look at the result. So query was, what are the internet speed requirements for remote work? So top 3 results with their score. So this time this is a similarity score, not the distance, because we have subtracted it from 1. So higher the score means this is ranking the 1, means this is more likely the response for your query. So it has performance review will be considered when evaluate. This part is not so significant, but after that you see it is speaking about the remote work policy. So this is the query, what are the internet speed requirement for remote work? The response is technology infrastructure, remote workers must have access to reliable internet connection with minimum speed of this much, download this much, and blah blah. This is the rank 1 and this is the rank 2 response. Then this here at the bottom you see rank 3. If you adjust this top k parameter here, you will get more results or less results depending upon the top k you have defined. So you have 3 results with their score. Now in hybrid retrieval, what we are going to do, we are going to do the similar thing. Additionally, we will refine the vector search or dense search with BM25 mechanism. So what is BM25? So BM25 is a mechanism for keyword search. It is mostly used in the web searches, for example. If you are going to search something over the net, various search engines use this mechanism. So it is not plain comparison or finding the keywords in the whole database or knowledge base. It has some algorithms that we are going to discuss in a moment. But why this number 25? Basically, researchers have been developing this best matching mechanism in various iterations. So there are like BM1, BM11, BM15, and the current is BM25. So we are going to use BM25. By the way, there are APIs to use that we are going to see in this cell. So how BM25 works? So it works on the term frequency. So we will have to understand what is term and what is frequency. So term basically called a word, and frequency, how often, how many times it has occurred in a document. For us here, the documentation is one chunk. So you can already guess that BM25 is not directly related to this retrieval system or RAG or AI at all. It existed again way before than this all AI stuff. But we are trying to develop a hybrid retrieval approach. You can think of various things, but I thought it might make sense to combine your vector search along with this keyword based search. We are going to see the scores, what have been achieved with BM25 and what is the achievement of vector search. So next, what is a query? You know, now the words are called query. Query term, a word from your search query. If you search, for example, internet is speed, the query terms are internet and speed. Next point to understand is diminishing returns. What is it? Suppose you are going to search something. If a document or a web page is found to have those keywords which are in your user query, most of the times, for example, with more than 100 occurrences, this is not necessary that that is the page you are exactly looking for, or that is the information or chunk of the information you are looking for. This likely keyword stuffing or spam, like Python tutorial multiple times. So it might be a spam. So that is exactly what is diminishing returns. With one occurrence in any piece of information, for example, this Python tutorial covers basics, clearly relevant. By the way, the query of the user is, he is looking for some Python tutorials, for example. So he gave input, for example, in any search engine, Python tutorial. So with any one occurrence, things are relevant. 3, 4, 5, 10 occurrences are more relevant. But 100 or more occurrences might not be relevant, maybe or may not be. So such things, this BM25 algorithms take care of. And next point to understand is the problem with linear counting. If we simply count occurrences, spam document that repeat words would always rank 1. So now you understand why this 100 occurrence example is not the thing, may not be the thing which you are looking for. So how BM25 solves this problem? It has some algorithm which creates the score of every chunk of the knowledge. It assigns a score, and whatever chunk has got the most number of score, that is returned to you by this function BM25. For example, one occurrence score 1.0, two occurrence is 50% increase, 3 occurrence, now it is not again 50%, it's only 20%. So as soon as the occurrences are increasing, the score is increasing, but not at the same rate. So there are more techniques which BM25 really uses to get you the best results according to the keyword matching. So we are not going really into each and every piece and algorithm which BM25 is using, but I'm just trying to cover the brief so that you have an idea about it. So next is key insight. So after 5 or 10 occurrences, additional mentions add very little value. As soon as the more and more occurrences are in the chunk or piece of information, so the curve actually saturates and becomes straight. Another important aspect about BM25 to understand is inverse document frequency, IDF. So it is how rare or common a term is across all documents. So this first term inverse is very important to understand. It is, what does this mean? It literally means opposite or reverse. So it doesn't really mean that the higher occurrences of a keyword in a document is more relevant. In fact, they are ranked lower and we want rare terms to score higher. So that is what it is implemented as. So document frequency, how many documents contain this term. So here are a few examples to understand what this inverse and document frequency mean. For example, the word the, THE, if it appears 1,000 times in a document, does this give you any kind of information? Does this add any value to what you are looking for? It doesn't really do that. So it has got a low IDF weight. That's what inverse is about. Another example would be a word called photosynthesis. If it appears only 2 times, for example, in a document which has got 1,000 words, it is highly specific to your query. For example, if a user is asking anything about photosynthesis and it has got a keyword in his user query itself, so the document, even if this keyword is appearing 2 times, it becomes highly relevant and it has got high IDF weight, inverse document frequency rate. So here is a formula. Formula uses the log calculation. So it is how the IDF is calculated. It is the log of total documents divided by document containing term. So it creates a map actually. For example, if user query is what is photosynthesis? So what is photosynthesis? So these 3 words will gain a score. Okay, what this keyword was found in that many documents, was found in that many documents, and photosynthesis was found in that many documents. So it creates that map. On the basis of that, it does calculate the log of total documents divided by documents containing a specific term. So this IDF score then again is calculated for each and every word in the user query. So here is an example how the calculation actually happens. You can have a look later. I'm going to publish it on the GitHub anyways. So another is document length normalization. That's also important. So problem is longer document naturally contain more words. So they have an unfair advantage. For example, if you are again searching for this word photosynthesis in a big book, it will appear many times. For example, in a book you found it for 1,000 times, but on a single page you got it for 10 times. Which is more valuable? Who should have more weight? So such things this BM25 algorithm or mechanism also sort out. Now why we should combine this embedding or vector search or dense search with BM25? BM25's strength, I believe by now you should be clear about it. It's the keyword matching. Of course, some intelligent keyword matching with a lots of algorithms inside it. And our embedding strengths, the vector search, how it works, it's a semantic similarity based search mechanism. So it searches by meaning, and another is search by keywords. Now you combine it and you have a highly accurate results coming out of your RAG pipeline. So if I expand this and try to run the code, let me expand it so that you can see the code. So this is how we can implement this. So this is the function. This is our query coming in. Again, top K, how many results actually you want. And this alpha, that we will see what alpha is going to do. So in this function, implement 2-stage retrieval approach. First, you will retrieve the results as we did in previous step here, simple vector search, and in vector search you have the score as well. And we will additionally do a BM25 search as well, and BM25 will also have some score attached to them. And then we will do a simple math. We will give 70% weightage to vector results and 30% weightage to BM25 results, and then we will re-rank the results based on these two scores combined together in a proportion of 70/30. That's what all this function is going to do. So let me take you through the code here. For example, step 1 is dense retrieval that you have already seen. We are going to embed the query first because query in the text cannot be compared to vector. So this was our vector store. I'm going to search for this in my vector store. So I'm going to search the responses for my query embeddings in my vector store. So these are vector store results, and extract chunk indices, and it is doing some arrangement in the data structure so that again we have not the distance but the similarity. Why we are doing it? Now you will get to know why we are doing a 1 minus distance and not relying on distance but the similarity score, because BM25 gives you the similarity, not the distance, so that both units are saying the same story. That's why we wanted to keep both the results score, the vector search result and BM25 result, in the form of similarity score, not the distance. So step 2, for by now here we have our vector search results. Now step 2, BM25 keyword matching. So how do we do it? Tokenize all chunk into words for BM25. So it's just doing, let me run it in the debug mode so that you can see what's happening in there. So step forward, it will run in the loop. Let me do it like this. So it did tokenized every chunk. So by the way, the chunks in vector search and in BM25, we are using the same chunking strategy. So please recall that the very first step where we created chunks, semantic chunking. So we are using the same method of chunking everywhere. Now we are in the hybrid search. So these chunks are converted into the small case and split by words because it's simply keyword matching. Now the query is also broken in the same way. The similar approach, we broke the query, or we converted our query into the embeddings because we had the vector embeddings. We had the vector store which had vectors or embeddings. So we did the similar for the query here. We had to, because our now this tokenized chunk is kind of vector store for us for BM25. So it's not a vector store, but this is, you can say, a knowledge base where BM25 now going to trigger the search. So this is how store looks for BM25. So similarly, queries are also broken into the lowercase and word by word. You can see it has broken. What are the internet speed requirement for the remote work? So now in the next section of the code, it will do a search of these query tokens inside tokenized chunks. As we did, to compare it again, as we did it for vector search, we had this vector store and we triggered a semantic similarity for the query embeddings. Similarly, we are going to trigger a keyword search in this store for these query tokens. That's simple. Both of the approaches are doing some kind of searching, but their mechanisms are different. So let me jump to the next line and let us see what it has got. It has also created a score of top 3 results. 431 means these are the indexes of the chunks which it found to be more relevant or which scored more. So here you see the numbers are floating again, but they are more than 1. In case of scores of vector search, they were from 0 to 1. So in the next step, to basically combine the results, it would be best that we further normalize the BM25 scores between 0 and 1. So step 3 is exactly what I said, normalize BM25 scores to 0 and 1. If I jump out here, so this is the original BM25 result and here is the normalized list. So it has normalized. Now what we are going to do is, we are going to do a simple math with the alpha score. Means 70% of vector search score will be considered and 30% score will be considered from BM25, and those scores will be combined and we will see out of these three which chunks rank first, second and third. That's all we are going to do in the next steps. So here you can see, here this is alpha into vector store, this is 0.7. So vector store results and now BM25 normalized results, both are, the scores both are between 0 and 1. So we will simply multiply by this factor, that is 0.7. It means 70% will be considered from vector store and the remaining one minus means 30% will be considered from here. And that's it. That's all you need to do. So you have APIs to do everything and you finally have the final results. That is hybrid result. So yes, so you have three results again. This is a hybrid score. And on the side by side, you will see what was the vector store result and what was the BM25 result. So BM25 result looks different than the vector store. For example, here if you see, this first chunk has got lower score from the vector score and it has got higher score according to BM25 search results. So that's why relying only upon one retrieval strategy is not so accurate all the time. Again, as I said, vector store score is less here, but BM25 is saying this is more matching. That's where we see the benefit of combining multiple retrieval strategies. Let me run this cell all together and we will see the final results. So query was again the same one. What are the internet speed requirements for remote work? Top 3 hybrid results were based on this rule: 70% semantic search and 30% keyword search, that is BM25, and this is vector search. And the rank 1 result is this thing, content is from here until here. It is not printing everything, just so that the output is not so huge that overflows this window. But you see the hybrid result, the vector result, BM25 almost 1, and the final hybrid result is 0.6, and this is the top ranker result out of your chunks according to user query. So this was all about the hybrid strategy. You can think more kind of retrieval systems, keyword matching, this BM25, it was just an example. You can combine multiple steps. Of course, they come on some cost. It might delay the retrieval every time you are doing some additional thing, but I haven't really done the benchmarking here, but certainly it will improvise the results. So if we go to the next section really is not about the retrieval part, but it's about query expansion. For example, users often ask queries in a way they don't match with any chunk, or they don't have any related information in your knowledge base at all. So it is better if you can rephrase the query. For example, how fast should my internet be? And in your document you are having minimum bandwidth requirement like text. So your RAG system, whatever it is, semantic or keyword based search, or if you have combined some more strategies for retrieval, there are possibilities that you do not get the exact responses. And another would be like WFH guidelines. This is work from home. This is the short form user have asked. And this is very much semantically related to remote work policy. But will your either semantic search or BM25 like algorithms will be able to identify such chunks? I'm not sure. Another example is what's needed for home office, and document has equipment specifications. They are unrelated from these two retrieval mechanisms point of view, but you know that from human intelligence you already know these two pieces of text are related. So what is the solution? You can just rewrite the query that has been supplied by user. You can expand the short forms in the query itself, and maybe you can rewrite the query in 2 or 3 forms and then shoot that query, single query or multiple queries, to your document store and then try to retrieve the results. So LLM is the best way to do that. For example, intelligent synonyms you can implement. You just need to send the user query to LLM with a simple prompt which can cater all these 4 points at least. If you have more in your mind, you can certainly add it to the prompt and LLM will give you the results what you want it to be. So you should really care about this intelligent synonym. For example, fast internet means high speed connection, broadband, bandwidth requirements. I mean, you can ask LLM to modify the user query. If they find such keywords, they can be expanded it like this. Acronyms, for example, WFH, BTW by the way, things like that. And contextual rewriting is actually creating more user queries which are semantically similar. How fast should internet be? Then internet speed requirement, minimum bandwidth specifications, these all are contextually similar things. And also at the end, for a single user query, you can ask LLM to give us 2-3 more similar or semantically similar or contextually similar things or user queries, so that you can fire them all together on the vector store, so that vector store can better relate and find the results. So if we go into the cell and have a look how to do that, it's simple. I think you have this LLM query expansion function here and prompt. Have a look at the prompt. You are a search query optimizer. Given a user search query, generate that many variations of user query. So we are going to generate multiple variations of a single query. Improved variation that will help find relevant document. Each variation should use different words, synonyms. Basically, this prompt is writing all the 4 points which we have discussed here. So you can write the prompt in your own words, but you have an idea how to expand the user query and how to run it. Just very similar. I will put a debug point. I will debug this cell. So it will do a query expansion here. I have used Grok Cloud service with which model I have used? Okay, 8 billion llama. That's enough. I mean, a basic model will do the job. And we have some query variations already. So what was original question? What are the WFH internet requirements? And what kind of variations we have got? We have got 1, 2, 3. What are the internet requirements for remote work from home setup? 1, 2, 3. These are generated by LLM. So next, for the demonstration, what I'm going to do is we are going to do a hybrid retrieval with the test query, means the original user query. Let us see what happens. The original result is something like that. It will be better visible in the cell output. So let me run it together. So have a look at the output. LLM-based query expansion, that's what we have discussed. User query was this thing. Now this is the demo 1. Retrieval using the original query. So the score was this for top 3 rankers. When we did the same thing which we have done in the previous cell, we did a hybrid search using the original query. Now what are the next things? It was the demo 1. Demo 2, retrieval using first expanded query. So we asked LLM to give us various number of variations of the original user query. So we are going to use the first variation what LLM has returned. That's what it is. So again, we have some scores here. And in the third demo, what I'm going to do is I'm just passing all the queries. That's what this multi-query retrieval system is all about. So what we are going to do is we are just using all the queries to get the best results, and we are printing the scores out here. And at the bottom you will see the table. Have a look at this. So this is rank 1, rank 2 and rank 3. These are the results of the chunks. So original query 6433. First expanded query, when we pass the first variation of the original query, we didn't pass the original query at all. We passed the first variation. Then the rank 1 was holding 0.68 and multi-query retrieval, this is 70. So these are the results. Certainly this I believe this is the same chunk and it got the highest score at the end. So far what we have done is we saw the vector search, then we combined it with the keyword search using BM25. Now to further refine our results, we went a step back and we said, okay, we will also expand the query in various forms using various strategies that we saw. Now in the next thing is re-ranking. That's another interesting part. Now what is re-ranking? What we have done so far isn't a ranking of some kind. That's also a ranking, but it is something advanced thing. So how we are going to do a further re-ranking? There are various approaches to do that basically. Cross-Encoder Reranking, that's what we are going to see in a moment. It is the most accurate and most commonly used approach as well. It makes use of some LLMs, the smaller LLMs, which can do in-depth analysis about the similarity and the context of user query with the chunks created out of a knowledge base. There are more approaches like LLM-based deranking and metadata filtering, but we are not going to look into each and every one, but only on this cross-encoder re-ranker. Let us jump into the code that will make more sense and give us more clarity. So what is cross-encoder re-ranking actually? So this approach uses a neural network to jointly encode the query and each candidate chunk. It is using neural networks, then predict a relevance score for each pair. This is much more accurate than simple scoring. As you have seen, this is not keyword matching. This does further in-depth analysis about the similarity using neural networks. So what we are going to do as a part of implementation is load a cross-encoder model. We can use, there are various available models to do that, but we are going to use this one. And the neural network is inside this model. As soon as you create this object, there will be a neural network and some advanced in-depth similarity algorithms will be executed and will give you the most accurate results among all approaches, I would say, which we have discussed so far, vector search and BM25 and the combined one. So this is the main function which does all the heavy lifting. Cross-encoder re-ranker, this is taking query initial results that can come out of your hybrid search or the dense search, for example. So you would have noticed that we are putting more and more mechanism on the top of one so that our results are more accurate. Like we had this dense search or vector search, then we combined it with BM25, then we went a step back and expanded the user query, and now on the top of the hybrid results or any kind of results, we are having one more option like this reranker. So what it does is, you will see here, so first it is preparing some pairs, query to the chunk. For example, you had a query and you got n number of results, so query versus chunks, this is preparing. So after those pairs, what is next? Get relevance scores from the cross-encoder model, and the model outputs a score for each query and chunk pair. So query is same, but the chunks are multiple, so it will assign a score for each pair. Higher means more relevant. So this is the similar protocol for our past retrieval mechanisms. So we use torch.noGrad to avoid tracking of gradients. So you see this line. So this line tells PyTorch not to track gradients while running the code inside it, basically this code. So a gradient is just the slope or rate of the change of something in machine learning. So basically gradients are required during the training of an LLM, for example. So we use this torch.noGrad during predictions. So we just want to make predictions to get the score for each pair of query versus its chunk, right? And where are the chunks? These are coming from initial results. These are, for example, let me check, where are they coming from? They are coming from the hybrid search. So we performed a hybrid search already, so we are having some results, and now we just want to do a prediction and we want to assign a score. No LLM training is going to happen, or no machine learning is going to happen in our case, since gradients are only needed for learning, not for making predictions. So we are just skipping gradients here. So, and the next line, score is equal to cross-encoder predict pairs. That's it. For each pair you need to assign a score, and this score is coming out of a deep analysis. This line asks the cross-encoder model to look at each pair of query chunk created here and give a number showing how well the chunk matches the query. The higher the number, the more relevant the chunk is to what the user asked. The scores are then used to sort and pick the best answers. So that's all what it is going to do. Rest of the code just prints everything in a manner so that it is easy to understand what happened. So step one is the hybrid search that has been performed. Very familiar thing which you have already seen. For example, hybrid score, vector score, and BM25 score. There are 1, 2, 3 top rankers. In fact, we chose to be 5 this time. Step 2, cross-encoder reranking. So now this is the cross-encoder score. Final is top 5 hybrid results sorted by cross-encoder score. So this is the cross-encoder score further combined with this thing. So in the step 2, this is cross-encoder reranking result and scores. Rank 1 is this, rank 2, rank 3. For example, this one is very far away matching chunk according to user query. So this is the final comparison being shown here. So this is not the combined result, but it is showing what was the result that cross-encoder did and how it was in comparison to hybrid score. For example, here it matches. So if you see the hybrid score, this chunk is scoring high and this is also scoring high according to cross-encoder score. Now this is the similar case here, but if you have a look at the rank 3 and 4, they do not have the same results or same scores produced by cross-encoder or hybrid approach. For example, the result from cross-encoder for the rank 4 chunk is less, but hybrid score is more. Here the hybrid score is less than this, but this is having a greater cross-encoder score. So these are not combined as we did in the previous approach, like using a alpha factor 0.7 or 70% from one and 30% from the other, but these are showing the exact comparison. Of course, you can implement the similar alpha factor here and combine the results. So this is not combined. So this is giving you very clear picture that one retrieval strategy may not produce the same score as another. So there has to be a wise combination of various retrieval approaches which you have in your implementation. So again, a recap, what we have done so far: we have seen the dense retrieval or the vector search. Number two, we have combined the results of vector search along with BM25. Then we thought, okay, can't we further expand the user query? Number three, we have seen a cross-encoder based implementation here. Next, we have seen cross-encoder reranker here. And then finally, we can think of context filtering. What is it? It is about a shortcoming about the vector store. If you have a vector store and if you have given the top k number to be 3, for example, and you ask it some query, for example, what is the policy about working from home, as we saw the example in our cells. If the vector store is created out of a, for example, car manual, it will still give you some results. And what you are going to have as an output, you can imagine that will be totally different things what user have asked and the results these are coming out of the vector store, because vector store is forced to produce some results at the end based on the top k, whatever you have decided, number 1, 2 or 3, whatever. So a context filtering is really important at the end. What you have asked and what you have got is really in the context or not. So there are various approaches to do context filtering. Here are a few. One, for example, similarity threshold filtering. So we have seen various scores produced by various retrieval strategies. So on the scores, we can put a threshold on the scores. As I have given you an example, like if a user asks for what are the work from home policies, and the vector store is created out of a car manual, so the scores are most likely to be in minus numbers. So the next one would be top n filtering. For example, return only top 3 most relevant chunks or piece of information out of my vector store, for example. Another is metadata filtering. For example, the metadata fields might be what is the document type, what is the user role, department and date. If a user want to retrieve any information for a certain time range, so that level of filtering should also be performed. For example, only show policy documents to HR users or any confidential document to a user who is authorized to see that. So such kind of metadata filtering you can consider applying. Another important point to consider is intent detection and filtering. Classify users' query to understand what kind of information they are seeking, policy, requirements, or troubleshooting. There are a few examples. For example, if I go in here, what are the troubleshooting steps for slow internet? So this is having a troubleshooting keywords already. So you should not show the chunks these are coming out of a policy document. For every chunk, you can create a tag. For example, this chunk belongs to a policy document. So you need not to show this chunk, even if it has a relevant information according to user query. So such kind of context filtering you can apply after the retrieval has happened. So this is another step about filtering or retrieving the information, so that this is exactly what user is intent or user is asking about and according to his authorization. So next point is about timeline filtering. If a user is specifically asking some information, for example, give me the policy of the year 2022 about work from home. So policies gets updated. You should always keep in context that user is asking specific information about a time period. So if you return the chunks from the year 2025, about the work from home policy, for example. It's of no use or might be misleading. So such things should be considered while retrieving the information from the vector store, for example. So basically, to implement this context filtering, there are various ways. You can either tag your chunks with specific keywords, with specific timelines, so that according to user query, these tags and timelines are matched also while retrieval. And also after the retrieval, you can further do the metadata kind of filtering as well, or the similarity threshold, things like that you can also implement after the retrieval. This is up to the user. So in this part we saw the retrieval strategies which could be there. There are some basic commonly used methods. That is very first one, the dense retrieval or vector search. Apart from that, I try to combine various approaches that can be useful while retrieving the system. You can further experiment with other approaches. The more accurate information out of your RAG pipeline you are going to augment and send to LLM, the more money you are going to save as a part of LLM token exchanges. That we are going to see in our next part. Thanks for watching.